Hi everybody, so today I'm going to be talking to you about the method of substitution. So this is a very important technique. We're going to be using this a lot for the rest of this course, and I think in Calc 2 and Calc 3, if you go on to take those courses, you're going to be learning to love the method of substitution because it's definitely going to come up over and over and over again. This is sort of like it's as ubiquitous as the chain rule is for derivatives. The method of substitution is for integrals. So first, I want to go over some terminology, and then we'll do an example, and I'll tell you what I actually mean by the method of substitution. But first, I want to tell you that integration by substitution is known by some other names. One would be integration by substitution. One would be u-Substitution, or u-sub for short. The third would be just substitution for short. And the fourth would be change of variable, or change of variables, or the method of change of variables, something like that. So these all mean the same thing, just different words that people use for this fundamental technique. All right, so moving on, I thought I'd show you the basic process and the method of substitution by computing an elementary example. So the basic process is we're going to be picking some function u of x. This will be our new variable. This is why the technique is sometimes called change of variables. This will be the old variable, x would be the old variable. And we're going to transform this integral, which has everything in terms of x, into some integral in terms of u. Then we're going to be able to compute this new integral easier than this old integral. So the first step of this process is to pick u, and we're going to pick u to be some function of x such that this integral gets easier to compute when we plug in u instead of x. So the basic idea here is that I know how to compute the integral of sine of x dx, right? I know how to compute that one. I've done it before. So similarly, I know how to compute the integral of sine of u du, right? It's just minus cosine of b minus cosine of a by the fundamental theorem of calculus, where a and b are our bounds of integration. So I want to make this integral look like this integral, and I'm going to pick u accordingly. So as you can see in the integral that I'm looking for here, I've got sine of u. So my u is going to be the inside of my sine function. So I'm going to take u equal to pi times x. The next step is to compute du by dx. In this case, du by dx is pi. The third thing is kind of funny. It's to find dx in terms of du. So du by dx is actually something that we can treat like a fraction. This is one reason that people like this Leibniz notation for derivatives, even though it takes longer to write than the Newton notation. So I'm just going to treat the top and the bottom of this du by dx equation as if they were their own variables, and I'll multiply through by dx. So I've got du by dx times dx equals pi dx. And then the dx and the dx cancel. So I'm left with du equals pi dx. Now, really, I want to find dx in terms of du, so I'll go ahead and isolate dx instead. So that gives me dx equals 1 over pi times du. The next step is to compute new bounds of integration. So the old bounds of integration in this problem are 0 and 1 over 2. So in my dx integral, I'm integrating from 0 to 1 over 2. In my new integral, which will be a du integral, I'm going to be integrating from u of 0 to u of 1 over 2. So I need to figure out what those numbers are, and I've got my formula right up here that I'm going to use to find those numbers. So u of 0 is equal to pi times 0, which is just 0, right? All I do is I plug in that value 0 for x in my formula for u. Similarly, u of 1/2 is equal to pi over 2. So my new integral, my du integral, is an integral from 0 to pi over 2 of some stuff du. So the next step of this process is to rewrite my original integral as the integral from u of a to u of b, f of u du. So my original function was in terms of x, now I want to write it in terms of u. In this case, my original integral was the integral from 0 to 1/2 of pi sine pi x dx, and pi x was equal to u. So this is equal to the integral from u of 0 to u of 1/2 pi times sine of u, because pi x is u, and dx is equal to 1 over pi du. So I will just substitute that in. right here. So now as you can see, this 1 over pi and this pi cancel out, and what I'm left with is the integral, and that's actually an integral that I know how to compute. So the last step of this process is to evaluate my new integral, and that gives me negative cosine of u evaluated at pi over 2 and at 0, which is negative cosine of pi over 2 minus negative cosine of 0, which is equal to minus 0 minus minus 1, so my final answer is 1. Okay, so now I'd like to show you another example. In this example, the problem tells me which substitution I should be using. So this isn't always going to be the case, obviously, but if the problem does tell you what substitution you should be using, it does make your life a little bit easier. So in this case, we can skip the first step. It's already done for us. U of x is equal to ln of x. And then the second step, we need to compute du by dx. Our third step, we want to find dx in terms of du. So du by dx equals 1 over x tells me that du is equal to 1 over x dx. So dx is equal to x du. My fourth step, I want to compute my new bounds of integration. So u of x is ln of x. So u of 1 is ln of 1, which is 0. U of e is equal to ln of e, which is equal to 1. So my new bounds of integration are 0 and 1. The next step is I want to rewrite my integral all in terms of u. So what that's going to give me is the integral from 0 to 1 of u squared, because ln of u is ln of x, and I've got ln of x squared, over x times dx, and dx is x du, and lo and behold, that x there and that x there cancel each other out, so indeed my integral is just in terms of u. So I've got the integral from 0 to 1 of u squared du, and the last step is to finish evaluating this. So an antiderivative is u to the third over 3, and we're going to evaluate that at 0 and 1 to get 1 over 3. Alright, so I've got one more example for you, and this time I'm going to give you some indication of how I would pick a good substitution u to use in order to make this integral easier to compute. So in this case, the problem is asking me to compute the integral of 8x cubed times the quantity x to the fourth minus 12 cubed dx. So in my integrand here, really I've got two terms. I've got a left term and a right term. So whenever you've got two terms in your integrand, and one of those terms has an inner function and an outer function, usually the substitution that you want to use is the inner function of the term that has an inner function. And usually the thing you want to do is check if the derivative of that inner part is anything like the other factor in the integrand. In this case, the derivative of my inner part is x to the fourth minus 12 prime, which is 4x cubed. And that looks a lot like 8x cubed, which is my other factor in my integrand. So that tells me that my inner function would be a good function to use for my u substitution. So I'm going to take u to be equal to x to the fourth minus 12. So now let's see how that computation plays out. So in this case, the problem is asking me to compute the integral of this function, and I identified that as a left factor and a right factor, and the inner part of my right factor is x to the fourth minus 12. So I'm going to try u of x equals x to the fourth minus 12. So the first thing I need to do is I need to find dx in terms of du. So I'll go ahead and compute du by dx. It is equal to 4x cubed. So that tells me that du is equal to 4x cubed dx. So in other words, dx is equal to 1 over 4x cubed du. And if I plug that into my integral, what it gives me is the indefinite integral of 8x cubed times u cubed 1 over 4x cubed du, right? Because that's the formula I just found for dx. So now I can simplify, and from there, this is just a simple computation, the same as we always did. An antiderivative is 2u to the fourth over 4 plus a constant, which is equal to u to the fourth over 2 plus a constant. Now we're almost done here, but this problem was phrased in terms of this variable x, and I'm the one who invented this variable u. So I shouldn't leave my answer in terms of this variable that I invented. I should rewrite the answer in terms of the original variable, so I'll do that now. And we're just going to use this same formula for u of x. U of x equals x to the fourth minus 12. So I've got u to the fourth here, so that means I'm going to take x to the fourth minus 12, and I'm going to take that whole thing to the fourth power, divide by 2, and add my constant of integration, and that is my final answer. Alright, that's all for today. I hope that you learned something, and have a nice day.